Recording is rolling. So it is Friday, October 21st. But you guys can turn your forecast. Thank you for doing that. I'll get those points in over the weekend. You guys have a take-home quiz I gave you yesterday. And you guys pick it up by Monday. All right. So let's wrap up this rotational type chapter. There's a couple of demos I wanted to hit, so let me hit those real fast, and then I'll get you guys started on a lab to get things to the weekend. All right, so LPs and CDs. This one thing I think is kind of interesting, so can't help but mention this. You guys know, like the old records. So you go back to the 1970s, had like big old discs. And then there was like a physical needle that came down. And now this was an invention by Thomas Edison, and or at least an adapted version of this, where like there are these physical grooves, and the needle like bumps up down as this thing rotates. Right, and that's going to translate back to the sound. Now, the way they would like the mechanics make this work is that this would rotate at a constant angular velocity, so it would turn at like constant rate. Right? Now this groove would spiral slowly in towards the center, so the needle will move. Right? But if you have a constant angular velocity, but a changing radial size, so like the needle starts out on the outside edge and it moves towards the inside over the length of the disc. Right? Then by the time you get to the middle, like one turn covers not as much circumference. Right on the outside, it's a huge circumference, on the inside, it's a small circumference for the same amount of time period. What that means is like the speed of the needle against the surface is actually variable. Right? Okay, so that's probably the easiest way to like manufacture this, like going back into the mid 20th century, right? Now, when CDs came along, like the digital version, what software engineers were thinking was, hey, we're dealing like zeros and ones, right? Like there's some laser now that reads zeros and ones. It goes from outside to inside. It's maybe like a trivial difference. But they're thinking, okay, all these bits, like bit, right? Each of those could represent like a 0 or a 1, right? Well, if we want to pack like the maximum amount of information onto a CD, then the linear speed of the laser against the surface would have to be like a constant value. But the only way to make that happen, now here's where things get crazy tricky, is that you actually have to have a variable angular velocity. So this CD starts out spinning, think how this would go, very quickly for like a first track when it's in the middle. Okay? And then when it gets to the outside tracks, it actually spins like more slowly so that you can have like a same number of bits per unit time. Right? Anyway, food for thought. You guys can think about that. Right, now you know. Another cool thing I want to mention is like hurricanes. We just had a hurricane come nearby us a couple weeks back, and if you look at hurricanes that cross Florida, they always spin the same way. They always spin counterclockwise. And I want to show you guys sort of why. Okay, let me flip the screen here. Screen 2. There's related to something called Coriolis effect, sometimes called Coriolis force, but it's not right. But it's really, it has to do with rotational motion. So these kids on a merry-go-round, they're going to pass around this yellow ball. And from our point of view, like helicopter point of view, the yellow ball only ever moves in a straight line, right? So you guys see that yellow ball just moving in a straight line. But of course, if you're on that rotating platform, that's not what you would perceive. So now if you go into the rotating frame of reference, so now we're no longer in an inertial frame of reference, right? The ball appears to be doing all this crazy like side-to-side motion, right? It looks like it's curving. Now, of course, it isn't really curving. It's only ever going in a straight line, and the entire platform is turning. Right? Is that right? Hey, aren't we on a giant spinning Earth? That's could be like a giant version of that. Let me show you guys some pictures of some hurricanes. Okay, so I've got some from like 2011. I want a snapshot of these. Right. You guys see like that counterclockwise motion, and then like this has like a counterclockwise type motion. Oh, there's Katrina. That's definitely counterclockwise. I've got one over Iceland that's not technically a hurricane, but it's the same type of effect, right? Just right, definitely counterclockwise. Okay. Now, why would that be? So let me switch back over here. Try to explain as quickly as best as I can. Okay. So, right, suppose you have a globe, right? And here you've got North Pole, South Pole's down here. Here's the equator. You guys know the Earth spins well left to right. Here's the way the Earth is rotating left to right, west to east, right? Right. So the Earth's going right now. If the Earth was not spinning, suppose you suppose you're up here on the pole, right, and you fire something like straight down. Right? Well, it's just going to go straight down. But if the Earth is spinning at the same time, do you see how if you fire something straight down, if the Earth is turning underneath it, right, as the object is going south, right, if you're on the surface of the Earth, see how it's going to appear to like drift off towards the east? Now it doesn't. It only ever goes like straight down. Right? But the fact that the Earth is turning to the east, right? I meant west. Right? Whoops. The Earth is turning to the east. Right? This thing's going to appear to drift off westward, which would be like, from the perspective of Santa Claus up here, would be look like it would tend to drift off to the right. That's what it's going to look like it's going to do. Okay. Now, if you start from the equator and you blast on the straight north, it's a similar type process. Right? The Earth is has a huge, like everywhere on the Earth has the same angular velocity. It's the same angular velocity regardless of your latitude. But there are different linear velocities, different v. Right down here on the equator, it's about 1,000 miles an hour, but at the pole it'd be 0 miles an hour relative to the axis of the Earth. Like here's the axis that's spinning around, right? Okay. So everybody has the same omega, but different angular velocity, or sorry, different linear velocities. Okay. So if you fire something straight north, well, it's coming from a latitude that has a huge eastward velocity to a place to latitudes that the ground underneath is not moving as fast, right? In linear terms, right? Which would also take some thinking, but it would make it tend to drift off to the right, right? So whether you're on the North Pole, you aim something straight south, or you're on the equator and aim something straight north, everything's going to kind of tend to drift off to the right, Ooh, see like hurricanes starting to set up here, right? Now, if you go down to the if you switch hemispheres, go down to the southern hemisphere, everything can tend to go to the left, right? Everything like reverses direction. You guys can think about that, right? But finally, to bring hurricanes together, hurricanes are low pressure systems, right? There's a bunch of warm water, a bunch of air evaporating, right? Evacuating spaces, leaving. If you look from above, like from satellite point of view, you see a giant low pressure. That's L for low pressure, right? Okay. So a bunch of air masses want to move in and fill that void, sort of, right? Fill that void. Right. And if the Earth was not rotating, that's all that would happen. It would be very exciting. But the fact that the Earth is rotating, the Coriolis effect kicks in. Right? You guys saw the kids on the merry-go-round. I saw that, put it all together. This is going to kind of tend to drift off to the right, relative to the spinning Earth. Same story here, 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 and here. Anytime you change latitude, that's the important thing, right? Right. And you guys see a hurricane being set up, right? That's why hurricanes form, and that's why they always spin the same direction. Let's say like counterclockwise in the northern hemisphere. Okay. All right. Hope you guys enjoyed that. All right, let's get to the main thing today. So I want to take you guys out with Turntable Friction Lab. So there's a bunch of turntables. I've got as many turntables back to the lab tables as I forgot. Oh, I'll give you guys this one too. But let me use this one for a demo real fast. Right. There's a bunch of little items back there. So just find some items. There's like binder clips. There's probably some picks left over from Songwriting Club. There might be like mountain. Pick your favorite item. I'm gonna use this because it's pretty classic. You only need one thing, right? Now let's watch here. Throw a couple on here. If I give this thing a spin, you guys know that the friction force is the force that's acting as the centripetal force that's allowing these to stay on the surface, moving in a curved path, right? If there was very little friction, then they would probably slip off pretty fast, right? Ooh, actually that tends towards the question we're getting at. It's like, well, how much friction? Maybe you could quantify that with coefficient of friction. Do you think there's a coefficient of static friction between this surface and this surface? Coefficient of static friction. Okay. Hey, and do you think that here, if I get the spin fast enough, ooh, the outside one went away, but now this one here's a holdout. Okay, and that one I had to get the spin really fast to get this one to move. Okay, so do you think that the rate that this is spinning and where it breaks friction and finally slides off, if you knew how fast it was spinning, and also its radial location from the center, that looks like it made a difference too, right? Because this one fell off pretty fast, and this one had to be spinning faster. So right now it looks like 5 centimeters from the center, and this one looks like it's 13 centimeters from the center, right? Right. So do you think if you could figure out how fast it's spinning to break friction and its radial location from the center, there's probably enough information just with that. It maybe also, Earth gravity, maybe that's important, right? That you could in principle calculate what's the coefficient of friction between the two surfaces, right? Now, you guys remember yesterday there was a couple of FRQs. We did one, and the other one we barely glanced at, right? I did put those back in your folders, and the way that FRQ went was they told you what the coefficient of friction was, and they asked for some other question. So, but it's really similar to what I'm going to have you guys do, right? Which is, can you figure out what the coefficient of friction is using this turntable method, right? You guys kind of get that, right? Now, I gave you guys a blank paper on your desk if you want to use that, or a lab notebook or your own paper. Now, my other classes, I gave them a very convenient table, said, do this, do this, do this, and then do this expression, and then boom, you have the answer. But you guys, AP, I want to see if you guys can figure this out yourselves. So go ahead and take the rest of the class, work with each other, and by the time you leave class, have turned into the gray tray, have coefficient of friction. You guys know the symbol for coefficient of friction, right? It's mu. And I guess if you want to be more specific, it's mu sub s. It's coefficient of static friction equals something. So have some calculations, right? Do you guys bring your stopwatches today? Right, because that might be very helpful today. Right, you guys got some rollers to done. You might want to take some rollers back there. That can help. Rollers, stopwatch, you should be able to do this whole lab. Right, so do some calculations. If you need paper, I gave you guys some paper. And at the very end, say coefficient of static friction equals something. Hey guys, what is a reasonable coefficient of static friction? Here, let me write some numbers down here. Suppose you and your teammates all come up with different numbers, and then you come up with these 3 different numbers. Which one of these is the only one that's a reasonable coefficient of friction? Yeah, I like this one here. Right, say the normal, or say the friction force could be 30% of the normal force. This one's way too small. That's like air hockey cable. This one's way too big. That doesn't make sense. All right. So you're looking for something kind of in this ballpark. You got like 0.65. Like, okay, that's reasonable. Okay. All right. All right. So go ahead. Everything you need back at lab table. And yeah, just turn that into the gray tray before you leave. Come up with a coefficient of friction between 2 surfaces.